welcome Michael Sutton, lead developer and core researcher of Kaspa, who will present Crescendo and Layer 1, Layer 2 ZK bridge overview. Welcome, Michael.
Hello. Nice meeting you all. I'm happy to be here. I was thinking it's a good idea to have Jonathan's talk before mine because he's bird eye view and giving a lot of context. But I also think our two talks are kind of have a cycle. Some of the information would be useful as a low-level information you would need to understand better some of the high-level concepts, but it is what it is. Yeah. Okay, so a short overview. I'm going to be talking about briefly Crescendo, which is the upcoming Kaspa hard fork. Accelerating the network from 1 BPS to 10 BPS scheduled for May 5th, which is 28 days from now, I guess. Around 5 weeks ago, we have successfully transitioned, implemented like the final rehearsal for the mainnet by simulating the exact same transition already on a testnet 10, which was operating on 1 BPS and successfully accelerated to 10 BPS. So I'll touch on that, and I'll speak about the overall design and architecture of the future L1, L2 bridge, and a very different angle than Jonathan. I'll zoom into some parts very technically, so I hope anyone in the crowd can take some insight, at least one insight, with him about this design, and I'll try to connect my view or some points in my talk to things Jonathan spoke about, hopefully, if I remember. So, yeah, atomic composable ZK-based rollup system as an endgame, which we might be arguing about later. L1 providing sequencing, data availability, and settlement. The fact that L1 provides sequencing and data availability, which is what we call based, is already supported by Crescendo, in a sense, without the settlement, without the ZK validity proofs. Actually, I'm presenting joint work with a lot of people, I think, starting with Roma here in the crowd, who I think was the first one to actually actively push and help me and Jonathan, in a sense, to build a zero-knowledge design with zero knowledge about zero knowledge, in a sense. Being able to treat zero knowledge as a black box, having him as an oracle. And throughout time, I found that to be useful. Me keeping myself a bit out of the zero knowledge details and staying zoomed out and focused on the overall design. So, Crescendo, this is, at the top you see the screenshot of the node at the activation moment, letting the operator know it has accelerated block rate tenfold. The DAG you see on the bottom is like a typical 10 BPS DAG. You can see a lot of block parallelism, but a very nice structure of a global peer-to-peer network communicating with 100 milliseconds block time. A lot of connections, a lot of edges. It's an interesting structure. So what's the point of 10 BPS? So first of all, just to be fast, throughput. Obviously, if you take the same block sizes and you make 10 of them instead of 1 of them in a second, you increase throughput. Unsurprisingly, maybe, you don't increase throughput tenfold. You actually might introduce some additional collisions in the process of creating more parallel blocks. But theory and practice shows this is a constant fraction of around 15, maybe 20% of the throughput. So you still get a nice 8, 9x TPS compared to 1 BPS, bringing us, if you speak about ordinary simple payment transactions, that would be 2,000 or 3,000 a second on Kaspa in a few weeks. While still running on commodity hardware, while still just requiring nodes to have maybe 8 cores, 16 gigabyte RAM, few hundred gigabytes disk, nothing more. Yeah, so increasing the block rate also means you increase the frequency of the system. The system is more responsive. You don't mine 1 block per second, you actually mine a block on average every 100 milliseconds, which means the closest you can get probably to humans' perception of blink of an eye. Transactions can be included like instantly, which is continuing to fulfill I want to ping my internet money and I want it to pong me back as fast as possible, as coined by GhostDAG. And like you spoke about, Jonathan spoke about MEV and oracles in previous talk. So increased block parallelism, although increasing some collisions, actually creates a more fair environment where there's more competition in the round. So you can think about it as intra-round censorship resistance maybe, or a very strong foundation for building mechanism designs that can make the system more fair. Besides 10 BPS, we also have a few significant upgrades, which were things that were developed throughout the last 2 years. Jonathan mentioned Storm, so that's also known as Keep 9, a solution for preventing state growth or state bloat at Kaspa's L1 state, not L2 state. So it's been adopted by the whole network on the mempool level for a year or so or more, but now it's actually being integrated into consensus, so being more secure, and also developed with more final details. Keep 10. Keep stands for Kaspa Improvement Proposal, in case you wondered. So Keep 10, introducing basic covenants by allowing a transaction to access its various fields, outputs and inputs from the script, so which gives the ability to build smarter script spending mechanisms or logics that can condition on what you're paying to. So that's why it would be called a covenant, because the spending script can control the receiving script, and henceforth can make sure you maintain some kind of logic, which would be the logical covenant of this script. And covenants are very essential for the future ZK proving verification on L1. So it's also related. And last but not least, in this context, is our Keep 14 and 15, which introduced 2 significant mechanisms that allow smart contract support over Kaspa very soon. So I'll get to that, of course. So that's Crescendo. So so giving another angle so Kaspa is trying to perfect the data sequencing and the data throughput scalability on L1. So we want to be fast, we want to be wide, meaning we want to have throughput, but we want to remain thin. We want to remain verification focused and not computational. We don't want all the expressiveness or the computational bottleneck to be on L1. So that's the state of mind. And with that, we come to the world of smart contracts, and it naturally leads you to this sweet spot of what is known as based rollups. But meaning we want all the L2s on Kaspa to use the L1 for sequencing and for data availability. So all the operations are actually going to happen on L1, and the interpretation will happen on L2s and be proven to L1. I find that it might be not appreciated enough. That when you just say based rollups, it doesn't capture the point. I think that the fact that you try to design a system where all L2s use the L1 sequencing actually means it's a unified consensus. There's unified consensus about the sequencing of the system. And if you manage to solve the scalability issue of the computational aspect, it's unlike, if you do that with non-based approaches, you're not doing a consensus system. So there's no limit. You're leaving one part of the triangle in a sense. You're not using security of L1. You're not using consensus of L1. Each L2 in a non-based world can add its own transactions in a sense. So there's no consensus. So it's not, when you scale that way, you're actually cheating in a sense. But if you manage to keep the unified consensus and also scale the computations, that's an interesting point. By the fact that all sequencing and data availability is on L1, you actually inherit the security and the decentralization from L1. So you actually also care less about the possible centralization of provers. You don't necessarily mind so much if provers are centralized or require a lot of resources, or even have a coordinated network of proving, because you get the security and decentralization from L1. So yeah. So going more, zooming more in. So the first challenge would be zero knowledge proving and verification is a two-sided protocol in a sense between the L1 and the L2. There's if you think about an Ethereum zero knowledge rollup, there's always going to be a core contract on L1 which represents the rollup on L1, and the provers actually interact with that contract. It defines what they need to prove and accepts their proofs in a sense. And because the L1, in the case of Ethereum, is a smart contract layer on its own, you can actually implement it in every creative way you wish. Although maybe costly, but you can implement any hash function, any verification logic, anything you want. So you actually have complete control over two sides of this interaction, which we don't have. So our life is not so easy. So we have an L1, which we don't want to make general compute available. We don't want to support general compute. So there's a challenge on how to design the zero knowledge verification side on the L1. So I'm not going to touch on all aspects of that, but I want to focus on one. I want to focus on what we call the sequencing commitment, which is probably the key to a lot of things, and also relates to some of the discussion afterwards. What is that, water? Thank you. Open it. So GhostDAG 101. So this is a, might sound a bit nuanced, but I think it gives, if you follow me on this, you might get some better understanding of what we're talking about. So this is a DAG. No cycles, just showing like a snapshot of like a few seconds in history. So the way GhostDAG orders the DAG is by selecting a chain, meaning each block selects one selected parent. And you also select the tip. According to amongst the tips, you select one tip with the same rule. So that actually induces a chain. The chain is selected based on accumulated proof of work of the blue cluster of Kaspa, which is a generalization of the idea of a chain to a more general structure, which still has constant width. So a blue cluster can be parameterized by K0, which would mean it's a chain, or it can be something wider depending on the BPS of the system and the latency assumptions. But however this chain is selected, it's selected somehow. And then we have, we can look at a merge set. So if we look at this block down here, let's call it D. So green arrow points at its selected parent, D tag. So the purple blocks are what we call the merge set of D. They are the blocks it merged into the DAG, and the other two blocks in the bottom are actually in the past of its selected parent. So it actually included them into the DAG. But this block D included these three blocks. So we call it the merge set. So the idea is we select this chain, and then we order the DAG by merge sets. So if I go one step further, you'll see that there's D. C actually merged another block, and B merged two more blocks. And we can induce an order from this mechanism. So we look at D, we take these four blocks, 1, 2, 3, 4, and then C would be the next block on the chain going forward, and it merged also number 5. And B merged 7, 8, and itself. So by selecting this chain and looking at the merge sets and the order, you get a total block order. And you can try and convince yourself that if the chain selection is robust, meaning if the chain only has reorg noise at the tips, at the constant width, at the constant depth from the tips, then also the ordering induced by the chain is stable. Just like because the ordering is a function of the chain. So if a part of the chain is already stabilized, so does the ordering induced by it. So that's what gives GhostDAG its security, actually, in a sense. So this is not illustrated as well, but think about each block in these 1, 2 to 9 as containing transactions. So the ordering of actual transactions would be induced by the block. So you would process each block by block, and any transaction which is legal within the context of that order is considered accepted as well. So by following the block order, you actually also get a transaction order, a transaction sequencing. So the main component we need in order to support zero-knowledge provers to be able to prove to L1 that they actually executed all transactions on L1 in the correct order. So we need to provide like a cryptographic primitive that succinctly represents the sequencing, the full sequencing. And for that, we define what the middle bullet, the commitment of block B, if we take the top one, would be, it's a recursive definition. It would be a hash over the commitment of its selected parent C, and a Merkle root of all transactions in the merge set of B, like from block 7, 8, and 9. So by defining this simple recursive structure, you actually have a single hash in each block, which is a function, a unique function of the complete ordering of all of its history. So each block now can have a single hash that cannot be altered and represents the full sequencing. And if you look at two such blocks, if we take D tag at the bottom and B at the top, so we're looking at all these blocks from 1 to 9, you actually can see that two commitments, the commit of D tag and commit of B, both uniquely describe a DAG segment, this specific DAG segment, and if you would change the order of each of these blocks, it would have produced a different commitment at B. And this segment is what can allow a zero knowledge prover to anchor its execution. So that's one part, like I described before, in Ethereum L1, when a user submits a transaction, which it's with the destiny being some specific rollup, the core contract on L1 would bundle it together with transactions provers need to prove. So we don't have that kind of custom mechanism that any entity can inject into L1. So we're trying to design a more general purpose structure where each prover can now choose its own granularity. It can actually choose how often it submits proof, because all it needs is the bottom commitment and the top commitment, and it can do it it can submit proofs once in an hour, or once in 10 minutes, or once in 10 seconds, hopefully. What happens is that a future proof transaction will point at D tag and B and provide a zero knowledge proof that it executed all the delta from D tag to B in the correct order. So that's one part of it. Another significant part of being able to support a zero knowledge proving system on L1 as the verification side of it is what I mentioned before, script covenants. So Crescendo includes basic covenants. We might need to extend the covenant support before zero knowledge is deployed. But it's the very covenants on L1 as a script combined with the idea of zero knowledge proofs are actually extremely powerful in the sense that they can allow you to maintain the state commitment of L2s on L1 in a secure way, unforgeable, and yeah, at the end you can see a link to posts you can read in length about this exact design. Speaking about a commitment, which is a hash of something, brings up the question related to what hash function to use in order to work with as many rollups as possible, which is there's a tendency between the efficiency of L1 computing these hashes and the effort needed by a prover on L2 in order to prove execution according to that hash. So that's something I think Roma is going to discuss. So if I want to zoom in on these sequencing commitments, so actually what we ended up doing following KIP 15 by Roma and Mike Zach is to support these sequencing commitments with the basic hash function already in Crescendo, and to add support for payloads, meaning transactions can, starting from a few weeks, can also carry arbitrary data. So combined, this means these two elements can be used to create based VMs over Kaspa without zero knowledge settlement yet. So there's no composability and a lot of missing elements, but nonetheless you can actually implement fully supported VMs. And the sequencing commitment, even though you're not going to use it for zero knowledge proving, it allows you to efficiently store only transactions in a trustless way, meaning because the sequencing commitment actually enfolds in it all the information about the full sequencing of all transactions in history, you can, in a way, forget about all blocks for a second. And an archive node can use this commitment, which is embedded into headers, so enforced by proof of work consensus all the time. So you can trust it by trusting L1, and you can actually reduce a lot of the storage requirements you would need for supporting a based VM without zero-knowledge support yet. So that enables, practically it enables smart contracts over Kaspa in the near future. Just want to mention, to emphasize what's the importance of zero knowledge in a based setup. Because if you can, we're actually saying it's based, so if you're not based and you don't have zero knowledge, then you're unrelated to L1. There's nothing linking you. But if you are based, so you're taking sequencing and data availability from L1, so what exactly does zero knowledge give you? You can still, you are still, if you're, the L2 is actually interpreting the state of the payload data going on L1, so anyone can execute it. It's kind of maybe a colored coin in the Bitcoin jargon. So what do you need zero knowledge for? So I can speak about three purposes. Yeah, three purposes. Maybe two of them are related. So the first one would be zero knowledge allows you to improve the reduce the trust of the system, meaning improve the trustlessness by storing state commitments constantly on L1 and having L1 verify the state transitions through zero knowledge proofs. You actually, for instance, one usage of it is that new nodes can sync using these state commitments. They don't need, they would not need to sync full history. So the bullet at the top where we're actually saving only on transactions would be needed maybe, but for new nodes and L2, you would only need to sync from a recent state commitment which was proven to L1, and you can get the full state of the L2, see that it matches, and start executing only recently without any trust. So zero knowledge proofs improve that aspect. Another critical aspect is a canonical bridge, is the ability to transfer Kaspa funds in and out of the L2. There's no way to trustlessly authorize a payment from L2, a transfer of Kas value from L2 to L1 according to some logic of a smart contract without being able to prove to L1 that I'm executing the correct contract. So there's no way to build a bridge transferring Kas in a trustless way without zero knowledge proofs. And having Kaspa being bridged to an L2 is significant in the overall economic design. So that's obviously a critical thing. The third point is the importance of zero knowledge proofs on L1. That's more about being on L1, is that L1 acts as a single trusted point of verification for the zero knowledge proof. So if there's n entities, you don't have to verify everyone else. It's L1 verifying all zero knowledge proofs. And then you can use that authentication or authorization by L1 to create more, to go on. So that's this. So before I go into atomic composability pretty fast, I'll touch on async messages. So I mentioned there's a future proof transaction, and it's pointing at these two bottom and top points and saying I'm proving to execute these transactions, and this is where my state on L2 went to, where the state transitioned to this and this state of L2 by executing these L1 transactions. And the proof transaction can actually emit an async message if it actually executed TXN1, which you see, and that transaction, when executed on L2, triggered some kind of message that is relevant to another proof system. So it would be output by the future proof transaction as an async message from TXN1. And we want to try to standardize this mechanism, so it's very easy for others to just see this message on L1 and know that it's authenticated and was sent by that specific L2, and the other L2 would not, the other logic zone would not need to do anything in order to verify the correctness of it, actually just going to get it as an authenticated message. So that's part of what I would call more of a standardization effort. So I must like touch very fast on just giving the basic preliminary. So a zero knowledge proof basic structure would be separated into two parts. The public inputs would be in the very basic case where I want a zero knowledge proof, a specific transaction. Let's say I have an L2, it has a global state before, G before, it has a global state. It has a global state before. I want to receive a transaction and execute it. So in order to zero knowledge proof it, I would build like this public interface which the verifier would, with all the minimal data the verifier would need in order to verify my claim, which that would include the hash of GB4, the hash of the transaction itself, the operation, and the hash of the global state after. And the private inputs, as a prover, you would need to actually provide witnesses to GB4 or parts of it and actually provide the transaction itself. And then you execute a prog and you show that you reached G after, which fits the hash of G after of the public input. And assume we have two rollups or logic zones, A and B, each with respective a prog. So this would be the sequencing of transactions. So most of them belong either to A or to B, but there's one transaction belonging to A and B, meaning the transaction touches both. I'll show you in a second. So this is related to something Jonathan mentioned. The fact that we are based is the only way this makes sense is because both A and B are going to follow the exact same global order of transactions. So when they both come to execute A plus B, they both have a pre-known and a deterministic state. So it makes sense to actually execute something together. And it can be proven because there's a deterministic way of executing. There's no two interpretations one can make. And if there would be another A plus B, and A would decide to flip the order and B would decide to keep the order, there would be no way to prove it because of possible cyclic dependencies. So in order to support atomic composable transactions, you actually need to have all rollups follow the exact same order and not do any reordering, which means you have to bake things like MEV solutions probably into L1 as the sequencer, and having one sequencer deciding also on the MEV prevention mechanism, and you can't delegate that to L2 conceptually. So you have this transaction A plus B, and I'll just use this as this slide is like a POC, a very basic idea, showing you that you can prove a composable transaction by relying on the subproofs of each. We're not breaking the scheme we described. I don't know if I described it in detail, but the scheme is that each logic zone would have its own proof chain, proving progress to L1. So we don't want to break that and say, okay, let's have A and B both prove collectively off-chain their transactions and submit one state commitment to L1. We want to allow the independency and only need to interact between provers when there is a dependency. So we want to keep the same outcome of a proof submitted of A and a proof submitted of B to L1, and somehow stitch them in a way that makes sense, such that when seeing both of the proofs, you can actually conclude both of them coincide, and you prove the state transitions of both of them simultaneously, even though you see them in separate parts. So if you look at this transaction call, you'd see like a smart contract call on A, starting execution. So I call this some transaction 1 up into the point where ownership of execution is transferred to the remote call to B as a remote call. So that it's defined as some transaction 1 because it ends by the remote call. So at the remote call is like passing the torch in a sense in a relay race where I'm actually going to ask prog B to prove its execution from this point until it passes the torch back to me. So we have 3 sub-transactions. And unlike the most naive scheme I showed before, which only has like public inputs hash before, hash of transaction, and hash after, you'd see that this scheme requires sub-transaction 1 to also commit to the hash of the local state of A, which it needs to keep in memory until the execution resumes. And it also needs to commit to the arguments you are passing to sub-transaction B, which receives the same argument and commits to the return value named vals. And then when operation resumes at logic zone A, you need to get the return values from the other logic zone and the hash of the local state, which was kept from before the remote call. So this would allow you, if you get a proof with these 3 proofs, with these public inputs, you can actually check that all links work. You actually try to build a DAG, and you would see that the commitments at the output of sub-transaction 1 match the respecting inputs at sub-transaction 2 and 3. And you would actually be able to build this DAG with matches. And you would be convinced that this execution is correct as a whole. This is a very basic scheme. A lot of details are not here, but I wanted to pass this somehow. Yeah, so it's a black box proof stitching. We're still targeting end proofs, so there's no zero knowledge aggregation. We're not actually trying to aggregate zero knowledge proofs into a single proof. We're trying to keep the proof separate, but still allow stitching. So there's a discussion about who the stitcher should be. I'm not going to go into, but it can be each L2 or the L1. Yeah, that's not for now. This specific, not only this, obviously, but so it's a joint formalization effort with GhostDAG and Fresher 08, mostly working on this one, but also anything else probably, including other people like Roma, Ilya, and probably others I forgot to mention. And I only touched here about the proving of the composable transaction, and actually hardly touched about the question who's executing the state and how do we actually get these intermediate states between the subproofs. So how would rollup A continue to execute the second segment without waiting for the proof of rollup B to arrive? So it needs to know the output of rollup B. So it either needs to execute rollup B itself or trust it, in a sense. So I'll just mention that if proof times are fast enough, you can imagine a reputation system where you're not risking too much proving effort because proofs are expected to happen maybe every 10 seconds. So even if someone is kind of lying to the states they're reporting to you, you can still build a lot of optimistic execution. You can rely on optimistic execution to drive the system to actually work. And yeah, I'm not going to touch on this. Okay. Some of the topics not covered in this talk are the canonical bridge details, hierarchic state commitments, all this list. There's a table of research posts. I hope everyone enjoyed. Thank you.